接下来的10:50至11:30将进行本日的第二场议程，此议程以英文来进行。This meeting will run from 10:50 to 11:30. Now let's welcome our speaker, Samuel Williams. He's going to share with us about the topic of event-driven concurrency using Ruby Fiber Scheduler. Now please join me in welcoming our speaker, Samuel Williams.
Hello, my name is Samuel Williams. Today we are going to be talking about event-driven concurrency in Ruby and how to implement it using the new Fiber Scheduler interface. Before we get to that though, I'm going to tell you a little bit about the history of its development and the 3 guiding principles that inspired the design. Finally, at the end of this talk, I'll tell you about the exciting new features we are hoping to deliver for Ruby 3.1. Ruby is a great language for software development and especially web applications. As Ruby's designers and engineers, we should look objectively at how Ruby is being used and where it could be better. Part of our role as core Ruby developers is to receive feedback from the community and build a meaningful evolution of the Ruby language. So how do we continue to improve Ruby? The area that I care about is scalability. I am driven by a deep desire to build simple, efficient, and predictable systems. Just as we design Ruby syntax and semantics for programmer happiness, I also believe that scalability should follow the same model. All too often, I find code in which scalability concerns were not considered, or the designs to achieve scalability are too complex, leading to bugs or other unintended consequences. Implementing robust, scalable programs in Ruby can therefore be a tricky problem, and this is what I would like to improve. I started working on Async, a gem for Ruby concurrency, in 2017. It was based on my previous experience with Celluloid and Event Machine. At the time, I was working on a DNS client and server implementation for Ruby called RubyDNS. DNS is not a complex system, but my early experiences trying to build scalable servers in Ruby showed me that there were a lot of tricky edge cases. I first started working on RubyDNS in 2009. Yes, it's over 10 years old and it still works today. At that time, it used 1 thread per server socket, which effectively limits us to processing 1 request at a time. I tried to run RubyDNS on my local network, and it quickly caused problems due to the limited scalability. It became obvious to me that DNS requests need to be serviced fast and concurrently. So in 2011, I reworked the implementation to use Event Machine. It worked fairly well, but Event Machine was a bit unstable, and this caused problems on my local network. On top of that, Event Machine's interface was completely different from native Ruby, so it necessitated a complete rewrite of the internal network code. At that time, RubyDNS could implement any kind of DNS query, including non-DNS systems like Wikipedia summaries over DNS text records. This required making an HTTP request to Wikipedia to get the summary. I tried several different HTTP clients, but all of them were effectively blocking. It was very hard to combine a server written in one library with a client written in another library and get good predictable performance. I became frustrated with Event Machine. The key interfaces for non-blocking I/O were unnecessarily unique, the lack of integration with other libraries, and for RubyDNS the final problem, missing IPv6 support. So I started looking for other options. At the time, Celluloid was gaining popularity, so I decided to try it out. Celluloid provides actor-based parallelism, along with an internal event-driven I/O per actor. I could wrap legacy blocking operations in one actor and invoke them from my event-driven DNS server running in another actor, using non-blocking message passing. This worked, but Celluloid actors are essentially globally addressable state. When I started updating tests for RubyDNS, I ran into problems where state from a previous test could leak into a subsequent one. I felt uncomfortable about a design which did not provide isolation. It was tricky to manage the lifecycle of actors, and this problem was fundamental to the design of Celluloid. Async was a kind of frustration-driven development. It was a response to the problems I had building RubyDNS. But those experiences were really important because they helped me formalize the core principles that I felt were important for a library that should underpin non-blocking applications, and ultimately informed the design of Async. The first core principle is isolation. The life cycle and state of the concurrent processing must be clearly defined and isolated. Async should provide clear and logical guarantees about its semantic model and avoid any kind of global state. It should behave predictably and reliably, even in the face of errors. The second core principle is compatibility. The non-blocking interfaces should match the existing native interfaces. Async should be a drop-in replacement, compatible with existing systems where possible. We should not need to introduce new keywords or methods except in places where the user explicitly opts into concurrency, and even these should be kept to a minimum. This is very different from other languages which do adopt new keywords for every non-blocking operation. The third core principle is stability. We need to define an interface that is simple enough that it can be very well defined with minimal complexity or edge cases. We should avoid opinionated models for concurrency which incur additional overheads. The core gems should be stable and have 100% test coverage. Extra functionality or ideas should be built on top using a layered approach. 3 months after I started development in 2017, the first major version of Async was released. Because the interface was so simple, it was easy to implement. We could reuse the best parts of Celluloid, such as NIO for the event loop. Async uses a layered design. The core interfaces are simple and straightforward. More complexity is added in separate gems which build on top of the core interfaces. Even early on, my expectation was that eventually we should be able to use native I/O, which is why all the I/O wrappers were put into a separate gem. Eventually, it would be unnecessary. The layered design gives a lot of flexibility with how we move the framework forward. Async embraces lightweight concurrency, breaking the user code up into tasks which run within an event loop. These tasks are built on top of fibers, which are cooperatively scheduled. Using wrappers around I/O, blocking operations can be redirected to the event loop transparently, so we don't need to change existing sequential code. Async also embraces parallelism in the form of threads and processes. We accept that CRuby has the GVL, and in many cases, the best way to achieve parallelism is to use multiple processes. We run one or more event loops per processor core. This allows us to build reliable, scalable systems that take advantage of all available hardware. The initial async implementation was not without some limitations. Native blocking operations could stall the event loop, including DNS resolution, waiting on other processes, native I/O, and external libraries performing blocking operations. In order to mitigate these issues, in 2018, I made a proposal to Ruby to introduce an interface for flexible cooperative concurrency. The proposal was for a set of hooks which redirect native blocking operations to a per-thread fiber scheduler. This scheduler can provide a non-blocking implementation of those operations. It took quite a lot of time and effort, including several trips to Japan, to get to the point where in 2020 we finally had a formal proposal. This was implemented and merged into Ruby 3. This was a major milestone for the project and one which establishes event-driven concurrency at the heart of Ruby. This month, we bumped Async's major version. We are preparing a new release which takes full advantage of the new Fiber Scheduler interface. It is completely forwards and backwards compatible. We will aim to release Async 2.0 along with Ruby 3.0.3, which includes some bug fixes, within the next few months. There are several interesting consequences of having event-driven concurrency built directly into a language. Existing applications, which are naturally asynchronous, like web servers, gain a new, more scalable execution model, fiber per request. But application code, in this case, does not change significantly. The concurrency is completely transparent. When developers explicitly opt into concurrent execution, things start to get a lot more interesting. Operations like fanout and MapReduce become very straightforward to implement efficiently and in a way that makes them easy to integrate across different libraries. But this isn't just about solving existing scalability issues. This is also about providing new ways of building Ruby applications, which are more natural in their design. We are liberated by the simplicity of concurrent execution, and this enables richer, more powerful software. As an example, here is a live debugger running from within the command line executable that uses async. It serves a web interface which renders the current internal state of the task hierarchy. This Async Debug gem can be dropped into any asynchronous system and shows that we can build real-time debuggers for complex concurrent systems. Another example is this implementation of Conway's Game of Life, written in pure Ruby, running in real time in a web browser. Falcon hosts the application, which runs over WebSockets. On the server side, we have an update loop, and this renders HTML which is sent to the web browser. It's not a revolutionary approach, but it does represent an evolutionary step forward for Ruby, and the fundamental design is enabled by event-driven concurrency. So how can we make our code execute concurrently? Let's take a look starting at the application code and how we can implement a very basic concurrent scheduler. We will start off defining our task with some blue part which represents processing and some green part which represents waiting on I/O. This is the time at which some other task could execute. Our sequential application iterates over a list of topics and does some kind of request for each topic. Firstly, we need to wrap each unit of work in a fiber. Now let's expand the request logic. First, we are going to make a connection to the service. Then, we are going to write a request. Finally, we are going to read a response. Now, let's make our read operation non-blocking. Firstly, we are going to change read to read non-block. Then, we are going to check the result, and if the data was not available, we will get the response wait readable. In that case, we will use a special system call, IOSelect, which waits until the data is available. This is the operation which accounts for the waiting time in our program. Rather than waiting, we can use another special operation called fiber yield, which passes control out of the current fiber and allows another fiber to execute. We store the current fiber into a waiting hash table, indexed by the I/O we are waiting on. Finally, we implement an event loop which waits for any I/O to become ready and resumes the matching fiber so it can continue execution. The execution of our fibers will be interleaved as they wait on different non-blocking operations, thus executing concurrently. We do not want developers to rewrite their code to use event-driven concurrency, as we have done in this example. So let's look at how we can build appropriate abstractions to hide the implementation details. Firstly, let's encapsulate the waiting list into a scheduler object. This scheduler will provide the interface required to wait on I/O and other blocking operations. We will use it to hide all the details of the event loop and the underlying operating system. Next, let's move the details of waiting on a specific I/O into the scheduler implementation. There is already a standard method for doing this called waitReadable. This allows the scheduler to handle the scheduling of individual fibers without the application code needing to explicitly yield control or manage the waiting list. Finally, we move the event loop implementation into the scheduler and replace it with a single method called run. This allows the scheduler to implement the event loop in the most efficient way possible. Going a step further, we can hide the entire non-blocking read operation. So let's revert the implementation back to the original read. We still need this to call into the scheduler. So how do we do this? In our implementation, scheduler is a local variable. We introduce a new special thread local variable to store the current scheduler. The thread local variable allows us to pass the scheduler as an implicit argument to methods that are invoked on the same thread, such as the read and write operations. If the read operation cannot return right away because there is no data available, in the C Ruby implementation, we will eventually end up in the RBIOWait function. At the start, we check if a thread local scheduler is set, and if there is, we invoke its implementation for IOWait. This is one of the most important fiber scheduler hooks for non-blocking I/O. The fiber scheduler has a few more abstractions to simplify its usage. When the program exits, we automatically run the scheduler if one is defined. This enforces the lifecycle and isolation guarantees and makes it easy to use correctly. We also introduce an abstraction for starting scheduled tasks. This allows the scheduler to manage how and when these tasks are created and executed. The most common model for this being right away and on the next iteration of the event loop. So now we know how the interface works. What about the real implementation of the scheduler? Async provides a complete implementation of the Ruby Fiber Scheduler. There are also other implementations of the Fiber Scheduler interface, such as Polyphony and libev Scheduler, which is really exciting. I love diversity of implementations, and it's one of the reasons why I designed the Fiber Scheduler as an interface, because I think that multiple competing implementations produces better long-term results. This is the implementation of the IOWait scheduler hook in Async. This is invoked from the non-blocking IO read and write methods when there is no data available. Internally, this method invokes IOWait on an object we refer to as the selector. It is called a selector because we use it to select some subset of operations which are ready to continue in a non-blocking way. Different operating systems have different implementations, so we need an abstraction here. At the top level, we have the run loop implementation, which is literally just a loop. Each iteration of this loop, we consider things like if there is work to be done, outstanding timers, and eventually invoking the selector's select method, which checks with the operating system if there are any I/O operations ready to continue. The select method is implemented by a new gem called event. It provides a high-performance, low-level interface for event readiness across several different operating systems. The most basic implementation uses a system call named select. This is the slowest, but also the most compatible option, and is provided by most operating systems. The select system call takes a list of I/O file descriptors and simply checks whether any of them are ready with data. If none of them are ready, it can wait. When one or more file descriptors becomes ready, it will return back to the scheduler implementation with this list. Let's take a quick look at the implementation. Like in the first example scheduler we created, we store a list of all fibers that are waiting on I/O. The I/O wait operation adds the current fiber to this list and transfers to the scheduler's event loop fiber. Selecting for events is relatively straightforward. Since we already have a list of I/Os, we invoke the select system call and wait. Once we have the list of ready I/O file descriptors back from the operating system, we then transfer to the waiting fibers which can continue execution and read the data. ePoll and KQ are very similar to each other. They can be more efficient than the select implementation because we can register the file descriptor with one system call rather than having to supply a potentially huge list of file descriptors every time we want to check for readiness. When we want to monitor an I/O file descriptor for events, we register it with the operating system and it stores it in a list. We can poll this list to check for any file descriptors which have become ready. The operating system returns a list of events which have occurred since we last checked. Recently, Linux introduced a revolutionary new interface called IOU-Ring. It allows us to submit batches of operations to the system with minimal overhead and handles an increasingly large number of critical system calls which would otherwise block with no non-blocking alternative. It works by having two asynchronous queues. One is called the submission queue and the other is called the completion queue. When we want to execute a blocking system call, we put it in the queue. When we are ready to check for results, we submit any outstanding items in the queue to the operating system. At some point after submission, the operating system will begin executing our request, and once complete, it places the result into the completion queue. We read the completion events out of the completion queue and transfer back to the fiber that was waiting. So, how does this all perform in practice? Well, we haven't got extensive benchmarks yet, but we have been using a simple one to look at the overhead of system calls and the cost of concurrency. This benchmark measures a single-threaded server handling web requests. On the left, we have a pure C implementation. Then we have the same implementation in Ruby. This shows us the overhead that Ruby introduces for what is otherwise a largely I/O-bound program. These three implementations come from the event gem. The U-ring selector is 63% the performance of the C implementation. The reason we lost a little bit of performance here is because we are allocating one fiber per request and every operation is non-blocking. Finally, we also compare with the current implementation of Async, version 1, which has a few additional overheads but is only 30% the performance of the C implementation. What's really exciting is that the new event loop gem has 2 times the throughput of the current Async 1 implementation. While we don't know the final performance, it looks like the fiber scheduler interface can provide a significant improvement on the current designs. So, you've heard about what we've done so far, but what comes next? What are we aiming for in Ruby 3.1? We have recently merged support for DNS address resolution hooks. This allows us to use non-blocking DNS resolution across all of Ruby. DNS is potentially a large source of network latency that we can now handle in a non-blocking way. This is a huge improvement. As you know, DNS is something that I'm passionate about, and so I'm very excited about this. Ruby 3.0 introduced partial support for non-blocking process wait, and in Ruby 3.1 we hope to expand this to kernel system, backticks, and other interfaces for running and waiting on child processes. This can be a huge advantage to build and packaging tools, which need to perform lots of concurrent processes. I'm personally really looking forward to using this feature. With the introduction of I/O U-ring, we get the ability to make the read and write system calls themselves asynchronous, which is necessary to implement non-blocking file system I/O. This requires a few internal tweaks to the Ruby I/O layer, but in essence allows us to deliver high-performance, non-blocking file I/O. This is especially relevant as underlying storage is becoming much more scalable and suitable for random access. Finally, I have been working on a new proposal to bring zero-copy, memory-mapped I/O buffers to Ruby. I hope we can integrate this into Ruby 3.1. It would be a massive advantage for native implementations of network protocols where the current string-based I/O is unnecessarily inefficient. Combined with I/O U-ring, we can minimize the overhead of Ruby's I/O system significantly, and this should improve the critical path for application servers written in Ruby. What are the next steps? We have a clear path forward to implement high-performance concurrent applications in Ruby, and we continue to push forward with new ideas and improvements. But it also depends on you, the community. Please try these new gems and features of Ruby and give feedback. The best thing you can do is have fun with these new projects. I hope they make scalability very exciting. And the businesses, please support this important work. We recently introduced a paid model for Falcon. If you are interested in this, please reach out. We want to support the Ruby ecosystem and help it continue to grow, especially in relation to scalability. If this is important for your business, you can help us develop it further by investing financially. Thank you for listening to my talk, and thank you to everyone who has made this possible.
Okay, thank you, Samuel Williams. Thank you for informative sharing. Now we are going to have Q&A session. Please feel free to ask any questions on Slido. The link are provided below, and we change to the page.
Excellent, thank you. Thank you for everyone who's interested in this work and my presentation. I hope it was interesting. So the first question, what is the cool tool you show in your presentation? So that tool, that is called Async Debug, and you can find that on GitHub under the socket tree organization. It's a tool that I have been thinking about for a long, long time. And I finally got to the point where I had all the pieces that I could combine to build it. So that was like async, WebSockets, a web server that I could embed in a process. Lots of pieces had to come together to make that possible. So it looks really simple, but it's not. And well, the implementation is simple, but all the pieces that had to go together to make it work required quite a bit of time. So it's called Async Debug. And so in any application that uses async, you can basically do this one line, which is async debug.serve. It will create a local web server running inside that process. Then you just connect to that and you can see like whatever's going on in your application. One of my goals for that, so the current sort of iteration is just a prototype, but one of my goals for that longer term is to make that more interactive. And so having like the fiber backtrace, having maybe breakpoints, having a way to log per... Oh, you can't hear me? Can you hear me? Sorry, can anyone hear me? Is this working?
Oh, I can hear you.
Oh, okay, great. Paul S.
I
just
can
said,
hear you.
Okay, good. Paul S. just said can't hear me. Look, apologies. If you want to reach out afterwards, I can follow up. Awesome. So Async Debug is a drop-in tool, and you can try it out, and I hope we can grow that and make it more exciting going forward. Okay, so question number 2. Would you mind to introduce how to use Falcon in production site? Okay, so Falcon is designed to be a drop-in replacement for like Puma or any other Ruby web server. The biggest difference between Falcon and Puma, for example, would be that out of the box, Falcon supports HTTP 2. And HTTP 2 requires TLS, which means that it runs over HTTPS, which means it makes a self-signed local certificate. And sometimes this trips people up because they run Falcon and they think it's running HTTP and they try and go there and get nothing. So basically, if you have an existing site using Puma, all you need to do is switch the gem from Puma to Falcon. And instead of running Puma, then you just run Falcon. And in theory, like it should all just work. The biggest limitations at this time with Async 1.0 or 1.x is that we still don't have full coverage of like external libraries that do blocking operations. And so one of the biggest challenges there, which a lot of people face, is Active Record. And Active Record, I hope, will embrace non-blocking concurrency, but it's not something which is currently working that well. And so because I've been waiting for them to make a move on this for like 3 or 4 years now, I decided to make my own database layer, which is completely event-driven, completely non-blocking. You can stream huge record sets, like millions of records. It's called the DB gem. If you want to make a non-blocking system using Falcon and you need a database, go and have a look at that gem. Okay, next question. Isn't process detach PID already non-blocking? That is a good question. So process.detach, my understanding is that actually creates a child process which is not bound to the current process's terminal, like controlling terminal. And so that allows you to fork off a daemon. I think that this model of doing daemon and non-blocking or like forking children processes is quite old, quite old style. And I think generally these days you'll be better off to look at systemd, which will handle all of that for you. So you just you write a process, you write logs to standard error, and then you tell systemd I'm a daemon, and systemd just takes care of all of that. In particular, if you're interested in this, there's a gem called Async Container, which integrates seamlessly with systemd and other process readiness notification systems, like just general shell scripts. And so what you can do is you can make an async program that sits within Async Container, and it will spin up one process per CPU core, and it will scale up your work as far as it can go. Is it possible to use Async WebSocket as an action cable adapter? Yes, people have been working on this. There is like 2 competing implementations. I'm not actually sure about these because I don't use Action Cable that much, but there are two different gems. I will put links to them in the Markdown document that we have on HackMD. Could you talk about an example of a on-copy, non-copy, and how it can be an issue? On-copy. I'm not sure I completely understand that question. So do you mind maybe either editing it or just ping me after the session, and I'll try and explain what try and give you an answer. Can you give hints on how to avoid potential race conditions or scope better file-based variable naming if they matter? Thanks. Okay, so this is an interesting question. So race conditions are a problem in any kind of program, not just concurrent ones. But concurrency and parallelism make the problems much, much worse. So I think that one of the things that I've been thinking about a lot is that in Ruby, we should try and protect the users. And I wanted to add trace points for detecting accesses to variables, both like class instance variables, local variables, all kinds of variables, even like constants. And the idea was if we could maybe track mutation to variables, we could determine if they were being mutated in a way which was done unsafely. This is something which is like much longer term. We haven't really like made any progress on this, to be honest. But there is one interesting pull request that just came recently, which is a trace point for constant access in Ruby. And so it allows you to call back whenever anyone uses a constant. And someone actually used this to implement like package scoped constants. So if you try and use a constant from another gem, it will tell you that you can't use it. So I think this is a really tricky question. Probably if you're really interested, I would recommend looking at the talk that I did at Ruby World Conference in 2019, I think, called Asynchronous Ruby. And I give like 5 examples of like potential race conditions. And I think I discussed those issues like in a lot more detail. So I'd recommend looking at that. If something goes wrong, will the entire concurrent process stop? It depends on like what goes wrong. So with async, when I was building that, I was looking at the kind of isolation guarantees that I would want in a real system. And I think when you look at this, the gold standard would be Erlang. Erlang has one of the most robust models for isolation in any language that I'm familiar with, at the runtime. And they do this on purpose because it's designed for cell phone towers that are supposed to handle like millions of phone calls. And, you wouldn't want one phone call taking out a whole cell phone tower or something like that. So with async, essentially every concurrent task is a promise in traditional kind of like concurrency. And so when you have a task and it breaks because of an exception, that task will raise an exception when you wait on it. And so it's very similar to Ruby's thread. When you have a thread which runs some user code, and that user code breaks with an exception, then when you try and join the thread, then the exception propagates out of join. So the way that async works is the exception model is per task. And if you wait on a task, the exception will propagate. So if you design a robust system, what robustness looks like from my point of view is if you have a server which is accepting connections, the exception shouldn't propagate any further than that loop, like the loop that is accepting connections. So every request that comes into your system, if that request like blows up for some reason, then that request is finished, it's done, but it shouldn't affect the server event loop at the top level. So in that sense, we try and have like certain reliability guarantees in async, and we try and model that in an isolated way. Could you provide a simple example of zero copy and how it affects performance? Yeah, okay, thank you for clarifying that. So zero copy is not something which I have actually got any benchmarks on yet. Where it gets really interesting is with IOU ring, because with IOU ring, you can register buffers into the kernel. And so what that means is you can pre-allocate, like say 1,000 buffers for IO. You can register them all into the kernel, and then you can say, here are all my clients, like WebSockets, like so long-running low throughput clients. And what the kernel will do is like basically write into one of those buffers and return back the data as part of the, as an event that's occurred in your system. So I don't think in Ruby that we will gain like a huge amount of performance from it because of it, but I think it will make Ruby applications more memory efficient and produce less garbage. one of the biggest issues we have right now with strings for I/O is that the guarantees around string mutability make them quite hard to reason about. So sometimes we end up like making copies of that string before we use it in an I/O operation. And so we do produce quite a lot of garbage within the Ruby implementation. We try and avoid it as well, but the way we avoid it is it's even more complexity to the whole system. So I kind of feel a little bit frustrated with like how it's currently working, and I sort of feel like we can continue to add like layers of complexity to try and solve these problems, or we can just go back to square one and maybe just use like a mechanism that is designed for I/O. And so what I'm really excited about is a simple, predictable memory map buffer, which we can use in a high performance I/O that doesn't have things like encoding issues, null termination. We have page aligned boundaries. We can memory map it so that we can provide, it can be memory mapped directly into the kernel space as well. These are all things we can't really do very easily with strings, as it were. So I'm personally looking forward to the benchmarks. We have a full implementation. There's a pull request on the CRuby GitHub repository and so you can check that out and have a look at that if you're interested. I would be really fascinated if someone was to take on board like doing testing or try and figure out the performance of it.
Okay. This meeting is reached our end, and thank you, Samuel Williams. Thank you for your informative sharing. And
you're most welcome.
Okay, let's take a short break right now. The next session will start at 11:35. Thank you. 接下来进入为期5分钟的中场休息时间，感谢讲者及大家的参与。下一场议程将在11:35开始，谢谢大家。Oh, that's cute cat. Okay, bye.